Hi everyone, welcome back. We're going to continue looking at triple integrals. In the last video, part one of this section, we started an example but didn't finish. So I just want to briefly summarize what we did. So we were asked to integrate the function x over a solid that was a tetrahedron. And then I went through the process of setting up bounds of integration. And I set up the integral all 6 ways. So to find the first set of bounds, first you choose a direction. You either pick z or y or x. You look through your solid in that direction to try to find 2 surfaces that bound that variable. So for instance, in the z direction, I'd move parallel to the z-axis. I'm always bounded below by the xy plane, and I'm always bounded above by this diagonal plane. So I bound z by the equations of those planes. In the xy plane, z equals 0, and this is the equation for that diagonal plane. Okay, now once you set up your first set of bounds, you don't need to use the solid anymore. You just need to project that solid into the appropriate plane. So the one where your first variable is 0. So again, if I had picked z to integrate with respect to first, I project this solid into the plane z equals 0, which is the xy plane, and I look at this 2D region here, and I come up with bounds for x and y. And now I have 2 choices. Do I start with x first or do I start with y first? But now this is kind of like setting up the bounds for a double integral like we've done before. So I did that for all 6 possible cases, and then I set up the integral 6 ways and said, okay, unless I specifically tell you to, or the book specifically asks you to, or the problem wherever it's written specifically asks you to set it up multiple ways, you only have to do this one way, because you're going to get the same answer no matter which one of these you evaluate. So now, let's actually look at one of these. So here, you see I've chosen to integrate with respect to z first, then y, then x. So these are the bounds that I need. Since the function I'm integrating is x, when I integrate with respect to z, I just get a z here, and then I plug in my bounds. I distribute the x, and now I just have a double integral, like you would have seen in section 15.2. So now I'm going to integrate with respect to y. Now I need to plug in my y bounds. When I plug in 0, everything disappears. And now I need to start being a little more careful. Right? Now things are getting a little messy because I have 6x times this line, negative 2/3 x plus 2, negative 2x squared times that same line, and negative 3/2 x times this line squared, negative 2/3 x plus 2 squared. So in the next step, I'm just going to take things a little bit slower, distribute these terms, and then I'm not going to distribute this yet. I'm going to actually square this term, which, remember, we're squaring a binomial, so it's 2/3 x plus 2 times 2/3 x plus 2, not 2/3 x squared plus 2 squared. That's incorrect. Okay. So now that's exactly what I've done here. I distributed over the first 2 terms to get these 4 terms, and here is where I've squared that binomial. Now in the next step, I'm going to combine my like terms, my negative 4x squareds here, and I'm going to distribute this negative 3/2 x, and this is the resulting polynomial. And then finally, before I integrate, I'm going to combine my like terms, looking at all 6 of these terms here. And I get the integral from 0 to 3 of 2/3 x cubed minus 4x squared plus 6x. And so now this looks much more manageable. So I go ahead and integrate. It's just a polynomial, so the integration is easy. I get 1/6x to the 4th minus 4/3 x cubed plus 3x squared from 0 to 3. I plug in my bounds. 3 to the 4th is 81, 3 cubed is 27, 3 squared is 9. And then I work this out, and I get an answer of 9/2. So this part of the problem is much easier. Once you have the integral set up, it can get a little tedious, it can get a little messy. You have to be careful with your algebra. You really have to be careful, make sure you're plugging the right numbers or the right functions into the correct places, working things out carefully, making sure that you're not copying down your problem incorrectly from line to line, making sure that you're not making arithmetic errors. But conceptually, it's much easier than having to set up the bounds. So really the hard part was in the last video. For triple integrals, a lot of the things we talked about for double integrals also apply. All of the properties we talked about where you can split up integrals or pull constants out of integrals, all of those things still hold. If I integrate 1 over a solid, I get the volume of that solid. This is similar to, for double integrals, when I integrated 1, I got the area of the domain I was integrating over. For single integrals, if I integrate 1, I get the length of the interval. For line integrals of scalar functions, if I integrate with respect to arc length and I integrate 1, I get the length of the curve. So that all is similar to what here, if I integrate 1, I get volume. If I want the average value of a function over a solid, I integrate that function over the solid and divide by the volume. So this is similar to what we saw for double integrals. I divide by the area to get the average value. Is what we saw in, I believe it's Calc 2, where you divide by the length of the interval to get the average value of the function in a single for a single integral. So it's a similar definition. And for triple integrals, if we have a separable function, meaning it can be written as a product of functions of single variables, so a function of x times a function of y times a function of z, we don't have variables in our integration bounds, then we can separate the integral like we did for double integrals. We can also use symmetry and even and odd functions, just like we did with double integrals. And I'm sure we'll see examples of that as we continue to look at triple integrals. So let's do another example to finish out this video. Find the volume of the solid bounded below by the paraboloid z equals x squared plus y squared, and bounded above by the sphere x squared plus y squared plus z squared equals 6. So now that we're talking about triple integrals, we're going to start seeing surfaces like this show up quite a bit. So it might be a good time to go back and revisit that page in section 12.6 that had all of the equations for different surfaces. If you're having trouble visualizing what your solid looks like, that's a good page to refer to. And that page in section 12.6 is page 754 in your textbook. So page 754 is going to be a good resource for surfaces, these quadratic surfaces. If you're not sure what your solid looks like, this will help kind of give you an idea. The first thing we want to do for this problem is to actually draw the solid, just like we did in the last example. So here's my version of drawing this solid, what it kind of looks like. That's about the best I can do right there. We have this paraboloid or a bowl shape in the bottom, and the top we have a piece of a sphere. Now I'm also going to take a look at this in Mathematica and show you a much better representation of this region. But before we go, it's going to come up later that I'm going to be interested in where these two surfaces intersect. So over here I've done a little work saying, okay, I'm just curious where these surfaces intersect. I'm going to need to know this information later. So where these two surfaces intersect satisfies both of these equations. So I want to solve a system of equations here. Well, since the paraboloid is already solved for z equals x squared plus y squared, and I have an x squared plus y squared sitting here, I'm just going to make a substitution, and instead of x squared plus y squared, I'm going to plug in z. So if z equals x squared plus y squared, then x squared plus y squared equals z, and I can plug that in here, and where these two surfaces intersect satisfies the equation z plus z squared equals 6. So then I can just factor this trinomial, and I get two solutions, 2 and -3. But only one of these solutions makes sense, because I know where these two surfaces intersect. Z has to be a positive number, or it could be 0. But x squared plus y squared is only defined for 0 and positive numbers, so the answer I want is 2. So these two surfaces intersect when z equals 2. And then I'm going to use this information later. I could find the equation for this circle where they intersect, and I'm going to do that eventually, but for now, we'll just leave it there that z equals 2 where these two surfaces intersect. Now let's take a look at a representation of this solid in Mathematica. You can see it looks a lot better than what I was able to draw. And let's start thinking about how or which variable we want to integrate with respect to first. So this solid kind of looks like an acorn. And if I start moving in the z direction, here's my z-axis. I move from the bottom to the top in the z direction. You'll see that I'm always bounded below by this paraboloid, and I'm always bounded above by the piece of the sphere. And so this is actually the variable I'm going to integrate with respect to first. Because if I decide I want to integrate with respect to x first, here's my x-axis. So I'm increasing in x, going from left to right, looking from this point of view. You'll see that down here, x is bounded below by the paraboloid and bounded above by the paraboloid. But if I go above where the two surfaces intersect, now x is bounded below by the sphere and bounded above by the sphere. So the bounding surfaces of my variable x change. So that means I'd have to set up two integrals. If I look in the y direction, or if I look at moving through this solid in the y direction, the exact same thing happens, right? So as I move through this solid in the y direction, in this region, I'm bounded below and above in the y direction by the paraboloid, but up here, I'm bounded below and above in the y direction with the sphere. So I'd also have to set up two integrals if I decide to integrate with respect to y first. So the best choice, or the easiest choice for this problem, is to integrate with respect to z first, because no matter where I look inside this region, I'm always bounded below by this paraboloid in the z direction, always bounded above by the sphere in the z direction. So I only have to set up one integral. Now, once we've decided that I want to integrate with respect to z first, I need to know what this solid looks like in the xy plane, or the plane where z equals 0. So I can look at this from above, and I'll cheat a little bit. And if I look at it from above, you'll see that this circle where the two surfaces intersect is actually the largest part of this solid. So if I look straight above, all I see is this disk that's bounded by the circle where the two surfaces intersect. So I do need to know the equation for that circle. And I know that z for that circle equals 2. So I'm going to use that information to help me figure out what this region looks like. All right, now let's go back to our notes and we'll look at all these things written down that I just said. We're going to integrate with respect to z first, because if we integrate with respect to x or y first, we're going to have to set up multiple integrals. Our bounds in the z direction were bounded below by the paraboloid, which was the surface z equals x squared plus y squared. We're bounded above by the sphere, which was x squared plus y squared plus z squared equals 6. So if I solve for z, I get the square root of 6 minus x squared minus y squared. And since z is positive for this solid, I only need the positive square root. Then I project into the xy plane, and I get this disk. I need to know what this circle is, so I say, okay, well, z, for this circle, z equals 2. I did that computation earlier. I solved that system of equations. So if z equals 2, I can plug that into the equation for the paraboloid, or I can plug it into the equation for a sphere. Either way, if I plug it into either equation, eventually I end up with x squared plus y squared equals 2. So this is the equation of the circle where the two surfaces intersect. This is also the circle that bounds this disk. So now this is a disk centered at the origin, bounded by a circle of radius square root of 2. I can decide which variables I want to integrate with respect to first, and I've set this up to integrate with respect to x first in this disk. And so going from left to right, I'm bounded by the left side of the circle below and the right side of the circle above. So it's bounded below by negative square root of 2 minus y squared. There's a mistake here that I'll fix. Bounded above by the square root of 2 minus y squared. Then once I'm done with my x bounds, I can just look at this region on the y-axis. It's going from negative square root of 2 to positive square root of 2, and there are my y bounds there. So now I have all of my bounds. I've only set this up one way, so I only came up with 3 bounds. And I set up my integral. And remember, we wanted to find volume, so I'm integrating 1 here. And first, I'm going to integrate with respect to z. And if I'm integrating 1, then when I integrate with respect to z, all I'm going to get really is the top bound minus the lower bound. And so that's exactly what I have here. Now I have a double integral, and I'm integrating the square root of 6 minus x squared minus y squared, and I'm subtracting x squared minus y squared. So this looks like a mess. I don't want to do this. One thing you could notice is say, well, I have an even function here, and I'm integrating over a domain that's symmetric in both x and y. So what I could do is just integrate in the first quadrant and multiply this integral by 4. So change these both to 0 and multiply by 4 by using symmetry. Instead, what I'm going to do is switch to polar coordinates, just to get rid of some of these square roots altogether. Now, I can't get rid of the square root of 2, because in this disk, the radius goes from 0 to the square root of 2. Since I'm going all the way around, theta goes from 0 to 2 pi. If you use symmetry, you could do the same thing and just let theta go from 0 to pi over 2, and then multiply your answer by 4. But I didn't set it up that way. Okay, if I switch to polar, I have my bounds for r and theta. I need to switch this function into polar coordinates. So this minus x squared minus y squared, both of these just turn into minus r squared. So now my function in polar coordinates is the square root of 6 minus r squared minus r squared. And don't forget, when we switch to polar, we have to multiply by r, because dx dy is r dr d theta. And now what I'm going to do next is I can separate this integral. I don't have any variables in my bounds. There are no thetas in this function, so I can just pull this d theta all the way out here, and that's exactly what I did. So this integral is just 2 pi, and now I need to evaluate this integral in r. I've distributed the r that I had to multiply by when I switched to polar, and I need to do a u substitution here. I've done u substitutions similar to this a couple times before, so I'm not going to write it out this time. But the idea is that u is 6 minus r squared, so I'm going to integrate u to the 1/2. I need a negative 2 here for my du. So I'm just going to go ahead and pretend there's a negative 2 there, and then when I integrate, I'm going to have a negative 1/2 left over, and I can integrate negative r cubed without much problem. So here's what I get. This 2 pi comes from this integral. This negative 1/2 comes from my u substitution. This 2/3 I'm dividing by the new exponent of 6 minus r squared, because it's 6 minus r squared to the 3/2. And then minus 1/4 r to the 4th is from integrating negative r cubed. Now I'm evaluating from 0 to the square root of 2. I plug my bounds in. This is what I get. And then you just have to simplify things. And I've actually written it 2 different ways. This is how I tend to simplify things, but I think the book tends to simplify things like this. It's exactly the same thing. It doesn't matter how you write it. The answer is exactly the same. So whatever feels best to you, that's fine. And that's the end of this example. So before we go, this is the end of section 15.5. I just want to reiterate that when you're setting up the bounds for these triple integrals, if the surfaces that bound your variable change, you have to set up multiple integrals. The same as we had for double integrals. If the curves that bounded your variable changed, you had to set up multiple integrals. The same is here. So you have to be very careful and really make sure you understand what's going on inside the region you're integrating over when you set up the bounds. Okay, in the next section, we're going to talk about integrating with respect to different coordinate systems, or what are some three-dimensional versions of polar coordinates.